Okay, so everyone should have a calculator, and today we are going over something really straightforward, and I would not expect any kind of difficulty that will be overwhelming. It's just a few steps. But today, though, we will learn something that is totally brand new, and we'll just have a little bit of exposure, and then later on after spring break, we will go fully into that concept. Now, so we have done X, Y coordinates forever, okay, and you are getting smarter and smarter as we proceed through these through these math courses. So now what we have been doing is called a rectangular system, which you will use X comma Y. Okay, I want you to write it down, like on the top right hand side, got some blank space right here. And what you would find out, well, what you're about to see today is that we are going to do something with what we call a polar coordinate system. And for this polar coordinate system, we do not use X or Y. Instead, we use something called R. Can you guess what R is? What R represents? I mean, we don't really use R often, so R, huh? Close, no. I mean, it could be like that, but another word. Radius, okay. So we have radius. And then we have something called theta, okay? Now, what is the benefit of this polar system? Now, you don't have to write the following down. Now, do you still remember back in geometry? You learned this, x minus h squared plus y minus k squared, sorry, y minus k parentheses squared is equal to r squared. Do you remember this equation? What's this equation for? Circle, right? And by the way, you should know this for SAT as well, right? Now, so we can do that, and but that's so many things to write down for a simple circle. So now we ask a question: can we have a simpler way to express things like a circle? I mean, circle has a radius. So let's just say I want to have a radius of 10. So all I need to do is to type in R equals to 10. Well, I think this is much better than writing down the x minus h squared plus y minus k squared equals to r squared. Just simply R equals to 10, then you have a circle. Okay, now we'll learn more about how to express them, how do we have different shapes later on in this course. Now, I also want to show you something too. So, so let's just say I want to make a flower. Actually, can make a flower. I can make a flower like this. Like this. All right. So, now this will be very difficult to make if you use the XY coordinate system. But with the polar system, it's a lot easier to make, and you will learn this later on in this course. Okay, so so that's just a little introduction of what we will see in the future. So we have radius, and we have this theta for this polar system. Okay, so so depending on what we are trying to do, we pick a better system to express. Now, what we will learn today is the representation of a vector. Yesterday, we learned about how to join the vectors together, how to find out the resultant vector. We can either add up the x and y, or we can find out the resultant by using the law of cosines. Today, it's simply about the representation of all these vectors. For now, I would say you won't really get the full appreciation of these forms until you take calculus 3, you actually do the vectors with calculus, and then you will understand why on earth we will do these kind of representation, because when you actually do those vectors, you would have to deal with matrices as well. And this kind of representation will be a lot easier to handle. So again, you won't get the full appreciation until you go to calculus 3. So what we do here, it's simply an exposure to what we will see in your future calculus class. All right, now, so over here we have the horizontal component and vertical component, and I believe that you should have done something like this back in physics, if you have taken physics already. So everything is based on one simple fact, and that is your triangle. This is x, this is y, this is your theta, this is your r. Okay, so just like how we did our unit circle, we say, oh, the x value is your cosine, because on a unit circle the radius is 1. But in this case, the radius is not necessarily 1, and therefore you have to multiply by the r. So that's why you have r cosine theta for x and r sine theta for y. So it's just a little extension of what you understood back in unit circle. So let's go ahead, let's find out the x component and the y component of the following example here. So we have a magnitude of 12. That's our r. That's the r value. And 53 degrees. Okay. So we can already draw a little diagram and says, all right, so 53 degrees is somewhere like here. So this is 53 degrees, and the length, it's the magnitude is 12. So if we want to break down the x and y component, we can already tell that it's going to the right, and it goes up. It goes to the right, and it goes up. So what we do, it's simply r cosine theta, which is 12 times cosine of 53 degrees. Component. So for the y component, it's 12 times sine of 53 degrees. So I'm going to let you put into the calculator and find out these two components. I can round it to 3 decimal places. Round to 3 decimal places. Okay, so if you need a calculator, make sure you get one here. 3 decimal places. So 12 times cosine of 53 degrees. So you would get 7.222. And 12 times sine of 53 degrees, you would get 9.584. Okay, so they are your x component and y component. Okay, so I think you do that for what in physics? Remember when you do projectile motion? Okay, when they give you the initial velocity, you have to break it down to the vertical velocity and horizontal velocity, and you know that horizontally there's no acceleration, so it's a constant velocity going straight. Right? So we have those. Okay. We'll talk about unit vector in just a moment. Okay, so so here, component form. Okay, so this is your component form. So you see, this is there's an I, it's a J. If you do 3-dimensional, we have a K, IJK. It's the same as X, Y, Z directions. Okay, the X direction is your I, Y direction is your J. Okay, So, and then the polar form, you have to find out the r, the theta. So we'll walk through those with the following example here. So here we have -5 and 12, meaning that we go to the left 5 units and up 12 units. So I want you to draw a little diagram like this. Okay, so so you go to the left 5 units and up 12 units. And this is one of the Pythagorean triples that you should know. What is the magnitude of the vector v? The magnitude of vector v should be 13. Okay, so that would be your little r, the radius. Okay, so this is your actual vector v right here. Okay, and then so for the component form, well, you just go ahead and instead of using comma, we use equation like kind of expression. -5i plus 12j is your vector v. Okay, -5i plus 12j. Make sure you put a little arrow above I and j to indicate that they are vectors. Okay. Now, what about b? Now, for b, we will need our radius and our theta. I think we have our radius already. This is our radius. So we got 13. But for x, we need our angle. And the angle is going to be this angle right here. Okay, so it's better if you can have a diagram to illustrate what the theta really is. But with the triangle, we can find out this angle right here, and let's call it theta prime. So if we can find out the theta prime, then we can find out the actual theta. So what we do here is to think about using theta prime with tangent. And I'm just going to do the 12/5 without the negative, because all I'm concerned about is the actual angle right here. All right, so 12/5, that's the angle. So you go ahead, use your calculator. So go ahead, find out what the angle is. Okay. Okay, this is our theta prime. Now this is a way to annotate because we have two angles. They are really closely related to each other. So I would use a little prime right next to it to indicate that it's the angle that's related but not the actual theta. So what's the angle here? Angle prime, the theta prime is 67.380 degrees. Okay. So if the theta prime is 67.380 degrees, then our actual theta would be 180 minus. So 112.62 degrees. Okay. So now you can put the angle right here. Okay, that is your theta. Okay. Plus 13 sine of, oh, I forgot to write down the I and J. All right, so don't forget the I and J here. All right, now I'm gonna let you write down first, and then I'm gonna elaborate a little bit more. All right, so now what I want to elaborate here is this. Now, I don't want you to just follow procedures. I want you to have a little deeper mental understanding of what's going on here. Now, these are just different ways of expressing the same thing. Okay, so this is -5. I want you to know that 13 times cosine of 112, the 112.62 degrees, it's the same thing as -5. If you don't trust me, you can actually go ahead and try on a calculator. And this is the reason why we do not put a negative in front, because the negative is going to come from the cosine right here. Since cosine of an angle in the second quadrant, it's going to give you a negative value. Okay, so they are literally the same thing. Okay, if I can highlight it, okay, -5 right here, it's the same thing as this. And then the 12 right here is the same thing as this. Okay, so just a little bit more work, but it's not hard at all. So just make sure you draw a diagram, knowing what angle you're finding and what is the angle of interest. And for part C is actually very easy. So for the unit vector, you can do this. Put the -5 and 12 first. And then we just go ahead and divide it by the magnitude, which is 13. Okay. So that's the unit vector. So we're basically shrinking it down so that the magnitude of the vector is just 1. And you can call this so this unit vector is basically a normalization of a vector. Now, again, you won't really get the full appreciation of the vector until calculus 3. But what we're trying to do here with the unit vector is that we are just concerned about the direction. We're not too concerned about the magnitude. So by doing this, it actually will allow your future calculation to be done a lot easier. Okay, so that's a unit vector. Again, just write down the x and y component, and then you just divide it by the overall magnitude. Okay. All right. So the following example, it's also very easy, similar to what you have done in physics, if you are taking physics or you have taken physics already. So we want to find out what vector v is, and we say vector v, it's u minus t. Yesterday, we drew it out. Today, we can just work with the numbers. So what's u? U, it's 10, comma, -7. What's t? -5, comma, 2. How do we get the vector v? Well, x component will operate with the other x component. So we have 10 minus -5, which gives us 15. And then the y component would operate with the y component. So -7 minus 2, it's -9. And that's the vector v. Okay. And for b, we basically do the same thing. So we have 4 times -5, comma, 2 plus 5 times 9, comma, 4. Those are the 2 vectors. And yesterday we drew a diagram. We had the 2 sitting in front of the vector. We say we double the length. And now we've got a 4 and a 5. Well, we do the same thing. We will quadruple. We'll quadruple the vector. Okay, here. So from -5, comma, 2 to -20, comma, 8. And then we have 9 times 5, which is 45. And then, sorry, 4 times 5, it's 20. And then you would add them together. So you would have 25, comma, 28. Okay, so really straightforward. Don't overthink it. It's very literal. You multiply that, you multiply the x values. Yes. All right. Yes.
On the first question with the IJK stuff, why do we use the I and the D?
Yeah, well, so when we do our matrices, okay, if you remember the last time you did matrices, it was Algebra 2 last year, we do systems of equations. So in the future, in Calculus 3, we would like to find out the what's it called? Some other vectors when two vectors join together. And with this kind of equation-like expression, IJK, that would allow us to handle the matrix calculation a lot easier. Yeah, so we're basically doing systems of equation in that sense. Okay. All right, now, so now the next two questions, they are a little like detective work. Okay, so the detective work is this. It's asking identify the pair of points that could be the initial and terminal points of the vector. So what's saying here, it's, hey, the vector here, it indicates moving to the left 2 units and down 8 units. So moving left 2 units and down 8 units. Which of the following points, which of the following pairs would indicate such that it moves to the left and down left 2 units and down 8 units. Now, I would say that choice A, it's out because the distance between these 2 points is not 2. Okay, -1 and -9, it's moving to the left 8 units, but we want to move left 2 units only. Choice D would also be out because the distance between 3 and -5, it's also 8 units, so it's too far away. So now we're down to a choice B and C. Now, I would say that to help you see this, it would be best if you can draw it out or sketch it out quickly and visualize it. So I'm going to sketch it out right here. So -5, -3, -3, -11. So we have a point right here, a point right there. Okay. So so if you if you join these 2 points, it's actually moving to the right 2 units and down 8, not to the left. So that means B, it's not correct. Okay, we want the vector to move left 2 units and down 8 units. So if you draw the part C, you have -1, -3, -4, -12. Draw these 2 points, connect them together. So you can see how it's moving to the left 2 units and down 8 units. So, yep. This one is moving to the right 2 units and down 8. So that's the difference. Right, so if you draw it out, sketch it out, it'll be a lot easier to plot. Okay. All right, number 2. All right, so the next detective work here is this. So we're telling you that the terminal point, it's at -7, -9. So this is the end point. And we want you to figure out the initial point. So we tell you the path. The path from the initial point is we move to the left 8 units and down 5 units. Okay, the path is moving to the left 8 units and down 5 units. So if it has moved to the left 8 units to get to -7, that means the original x value must be a 1. If it moves down 5 units to get to -9, that means the original value must be -4. So the point is 1, -4. So you just need to trace backward. Okay. If you understand what it means, it's very straightforward. All right, now, using the examples that I've done for you, can you go ahead and finish number 3 and number 4? All right, go ahead, finish number 3 and number 4. All right, so for number 3, we have our magnitude, which is your r, and we have the theta, which is your 240. So for the x component, it's simply r cosine theta, which is 24 cosine of 240 degrees. I don't think you need to use a calculator for this one. For y component, it's r sine theta, which is 24 sine of 240 degrees. And for this one too, I think the angle is very nice that you do not need to use a calculator. What's cosine of 240 degrees? Negative. Cosine 240, negative 1/2. Okay, which gives you negative 12. And then what is sine of 240 then? Negative root 3/2, which gives you negative 12 with 3. Okay, so these are the x and y components. Okay, so for nice angles, you do not use a calculator, but for other ugly angles, you would need to use a calculator. And then for the bottom one, for number 4, now go ahead, sketch the diagram here. So we have the vector v going to the left 6 units and down 8 units. So so negative 6, negative 8. So this is the actual vector right here. This is your vector v. So if I ask you, can you quickly tell me the magnitude of vector v? What is the magnitude of vector v here? If it's a 6 and 8, then the hypotenuse must be 10. Okay, the magnitude must be 10 because of the 3, 4, 5 triangle. Okay, you just double everything right here. So for the component form, it's very easy because for the component form is just minus 6i minus 8j. Okay, that's the component form. Okay, now let me go ahead and finish the unit vector as well, because the unit vector is also very straightforward since we know our magnitude, which is 10. So, and we need to simplify it. So we have negative 3/5 over negative 4/5. But now let's go back to the polar form. The polar form is going to be the radius, which is 10, cosine of the theta I plus the radius times sine of the theta j. So now the question is, what is the theta? Well, that's a starting point, right? So our theta will be right here. That's our theta. But with a triangle, we can go ahead and find out this angle first, and let's call it theta prime. Okay, so we say, all right, let's go ahead and do the theta prime. So we can say tangent of theta prime is equal to h/6. We just want an angle. Okay, tangent theta prime, it's h/6, opposite over adjacent. Okay, which is 4/3. So theta prime would be, so we take the inverse tangent of 4/3, and that gives you 53.130. And if the theta prime is 53.130, the actual theta will be 180 plus 53.130, and that is 233.130 degrees. So that's what we put into the theta right here, 233.130 degrees, 233.130 degrees. And that's how we express the vector in polar form. Okay. So, yeah, so whenever you do a unit vector here, make sure you simplify if it could be simplified. Do not let something like this to sit around like -6/10. They don't look nice at all. So my major concern, my major concern right here is that are you actively drawing your diagram? Are you labeling, annotating the diagram properly? Okay. Do you know how to find out the actual theta using the triangle as a little help? Okay, and when I do the triangle, I don't really care about the sign. Okay, even though for this case, the negatives would get canceled out, but we don't really care about the sign because we just care about the angle itself. Okay, we just care about the angle of the triangle. So, so in this case, it will be 180 degrees plus the theta prime to get us the actual theta. Questions?
Wait, so you're not finding the angle, or you're not gonna like, so instead of it being on the other side, you have to add that angle.
Well, depending on now, if you say the actual theta, now let's just say the okay. Let's say this is the actual vector. Okay, so the vector moved to the right and down. So the actual theta, it's here. But what you would do, you would find out this part right here. Let's call this theta prime. And you do 360 minus the theta prime to find out the actual theta.
Wait, why are we finding the theta there on the
Because for the polar form, we need the theta. For polar form, the expression is r cosine theta I plus r sine theta j. So we need to insert the values for the r, and we need to insert the value for theta in order to complete the expression in polar form.
How do you know which like side to find theta? Like on the previous problem,
Mm-hmm.
like
Mm-hmm.
the other side of the triangle, so I have to do something.
Now, because what's given, now in reference of that theta prime, what's given to us? Opposite and adjacent. So that's why we use tangent. Okay. Can we use sine or cosine? Well, in that case, you will have to use the hypotenuse. If you are 100% sure about the hypotenuse length, that's fine. But our habit is to use the given values to minimize the risk of getting something
I know
wrong.
that, but like you added it to
180?
yeah, you added it to 180.
Because it's in quadrant 3.
Oh.
Right? It's in quadrant 3. So so you know this is 180, right? You know this is 180. And then you tag on this little angle. So that's why.
Okay.
Yeah. So if you have a diagram, then you understand why we are adding and subtracting. If you don't have a diagram, it's going to be difficult to determine.